Hello everyone, I'm Yusun, come from the Idea Lab at UNC. This time I will share our work with you, that is, semi-supervised transfer learning for infant cerebellum tissue segmentation. First, let me introduce some background of our work. So, what is cerebellum? This is a real brain, and the right figure is the corresponding MLMI image. The red color region denotes cerebellum. Cerebellum plays an important role in motor control and is also involved in some cognitive functions, as well as emotional control. In this slide, I will introduce the current research status about infant cerebellum segmentation, compared with cerebellum segmentation. There are very few works proposed for infant cerebellum tissue segmentation. For example, the ensemble-sparse learning method and theories. And to the best of our knowledge, there is no work on cerebellum tissue segmentation for infant subjects less than 24 months of age. We can see the left figure. As the subject grows, the tissue contrast gradually becomes high in the T1 and T2 weighted image, especially for the 24-month-old subjects, which are easier to be added to obtain manual labels. However, directly applying the model trained on 24-month-old subjects to younger infants cannot derive satisfactory segmentation results. As shown in the third column, there are some unreasonable results are cycled by red lines. Therefore, in this work, we proposed a method to improve the cerebellum segmentation. And we should note that only 24-month-old manual labels are used for training. Our dataset comes from the UNC Baby Connectome Project, shortly as BCP. There are some information about the dataset. Now, I will introduce our proposed method. This is our flowchart, which consists of 3 stages. The first stage is training a segmentation model with 24-month-old subjects and manual labels. The second stage is how to choose unlabeled images from other month subjects for training. And the third stage is how to retrain the segmentation model for other months. In the next time, I will detail these 3 stages. The first stage is training segmentation model for 24-month-old subjects. We apply the AD as the architecture, and the inputs are T1 and T2 weighted images and manual labels. We use the death ratio to evaluate the performance of trained model, and the death values are all over 19%. The second stage is automatic generation of training labels for younger month-old subjects. For the 24-month-old images, after generating the segmentation by trained model, we can obtain error map by comparing the difference between segmentation and ground truth. Then the segmentation and error map are used to train the confidence model. The reliability of automatic segmentation can be indicated by the confidence map, as shown in this figure. We can see this region. Then, according to the confidence map, we can order these unlabeled images to choose top key subjects as training dataset for other months. The last stage is retrain segmentation model for other month-old subjects with the selected training images. Note that, in order to pay more attention to reliable labels, we propose a specially weighted cross-entropy loss, which uses confidence map as weight. There are some experimental results. The first experiment is selection the number K of training subjects. As we discussed before, we chose top K subjects as training site. But which is the number K? We set this experiment to choose it. In this figure, the horizontal axis is number K, and the vertical axis is death ratio of tissue segmentation. We can know that before number 10, the death ratio is gradually increased, will becomes decreased after number 10. Thus, we choose K equals 10 in this work. Then, we want to know if the selected K unlabeled images are helpful to improve the segmentation performance. Then, we make a comparison between semi-supervised learning, denoted as the blue bar, and supervised learning, denoted as the yellow bar. The horizontal axis is training number. As we can see, the death ratio of semi-supervised learning is higher than that of supervised learning, which indicates that the unlabeled images are helpful to improve the performance. We further made an ablation study to show the importance of the proposed loss function. We can observe these regions indicated by red arrows. Obviously, the results of proposed spatially weighted cross-entropy loss are more consistent with ground truth. The last one is the comparison with other methods. The first and second columns are T1 and T2 weighted images. The third column results are obtained using Wolverine software. The fourth column shows results of ADO9, and the results of our proposed method and ground truth are shown in the last two columns. These red lines circled some results which we can compare the method's performance, and also this. This is a table shows positive results, and there are some death ratios of cerebellum segmentation results on testing subjects at different months of age. The cross symbol indicates that our proposed method is significantly better than other methods. In this work, in order to deal with the challenging task of infant cerebellum tissue segmentation, we proposed a semi-supervised transfer learning framework guided by the confidence map. And these experiments demonstrate that our proposed method has achieved a significant improvement in terms of accuracy. And we will further extend our method to newborn subjects and validate on more subjects. Thanks for your attention.